For decades, computing relied on explicit logic. We told the machine exactly what to do, step by step, using rigid code. Today, the computer interprets raw context to determine its own execution path. In the traditional era of Software 1.0, programmers wrote every rule and syntax. Software 2.0 shifted that work to neural network training, where we arrange datasets rather than lines of logic. We have now entered Software 3.0. By training large language models on the vast multitasking environment of the internet, the model itself has become the programmable computer. Your primary lever over this machine is the context window. Frontier AI labs are dictating the capabilities of this new substrate. As they scale these models, the ability to process information and execute workflows changes fundamentally every few months. This shift enables vibe coding, which lowers the barrier for beginners to generate software. However, professional engineering, which requires security, scalability, and quality, now relies on agentic engineering, the discipline of coordinating stochastic models to meet a professional bar. Mastering this requires a shift in mindset. To build reliable software today, you cannot treat the LLM as a human developer. You must treat it as a machine with specific physical limitations. The defining behavioral trait of this machine is jagged intelligence. Unlike human experts, these models do not have a uniform level of capability across related tasks. This topographical map illustrates the model's competence. Through reinforcement learning, these models develop sharp capability spikes in domains with strictly verifiable output, like math and code. Adjacent to these are deep valleys. In areas requiring subjective reasoning, performance can collapse without warning. State-of-the-art models can refactor a massive codebase to find zero-day vulnerabilities, yet simultaneously fail to realize a person should walk 50 meters to a car wash instead of driving there. This jaggedness is why traditional software delegation fails. If an agent isn't constrained, it will eventually wander out of a capability spike and into a logic valley, producing hallucinated results. Professional engineering requires pinning the agent to the peaks. You must ensure the model only operates within domains where its logic can be instantly verified. Navigating this landscape means abandoning open-ended instructions. Instead, you must build workflows centered on aggressive, automated feedback loops that catch errors the moment the machine drifts. The first physical constraint of the Software 3.0 machine is the context window. This graph shows reasoning efficacy dropping as you add data. Because internal attention scales quadratically, logical coherence plummets. It starts in the precise smart zone, but as the context window fills, the model enters the dumb zone, where reasoning becomes computationally chaotic. Operating in the dumb zone leads to compounding errors. The agent loses track of variables, hallucinating logic to fill the gaps in its attention. To prevent this, you must treat the model like the protagonist in the movie Memento. It is inherently stateless. Every time you clear the context, the machine wakes up with no persistent memory of the previous call. Human engineers rely on long-running mental threads to manage large projects. Agents cannot replicate this. Their efficacy is tied to the immediate, fresh context window. Workflow rules must enforce this statelessness. To maintain peak competence, an engineer must aggressively clear the context window and reset the agent to the smart zone before every new task. Preserving that fresh state is the fundamental requirement for reliable code generation. If you manage the context, you manage the output. Standard software management relies on specs to code, handing a static document to an engineer. In the agentic era, this approach results in misalignment. You need active design alignment instead. Before writing code, you initiate a grill me protocol. You force the AI to aggressively interrogate you about every unstated dependency and architectural decision. The AI identifies edge cases you haven't considered. Your answers refine the plan into a rigorous product requirements document, or PRD. This phase requires your full attention. Alignment is the one part of the process that cannot be automated. It requires human domain expertise to prevent the agent from making disastrous, hallucinated assumptions later. By securing a shared design concept up front, you eliminate ambiguity. When the agent eventually executes the code in isolation, it is following your verified map rather than guessing. Once the plan is aligned, you must structure the tasks for the agent. Delegating work horizontally across a codebase is a guaranteed failure mode. If you ask an agent to delve an entire database layer first, it is working blindly. Because the API and front-end don't exist yet, there is no way to verify if the code works. There is no feedback loop. This lack of verification causes the agent to drift. It fills its context window with thousands of lines of unverified horizontal logic, drifting deep into the dumb zone before a single component is functional. To maintain reliability, you must divide the PRD into vertical slices, also known as tracer bullets. A vertical slice builds a thin sliver of the schema, the service logic, and the UI simultaneously. You anchor this process with test-driven development. The agent writes a failing test first, then writes the minimum code necessary to make it pass. This gives the model the immediate, verifiable feedback it needs to correct itself. Pairing vertical slices with TDD keeps the AI anchored and its capability spikes. It completes functional units of work without ever bloating the context window. Managing isolated tasks only works if the codebase architecture itself is designed for AI readability. To maintain reliability, the underlying structure must support the agent's limited context window. Many traditional codebases rely on shallow modules, hundreds of tiny files with complex, interwoven dependencies. Fragmenting logic this way breaks the agent's understanding of the system. It cannot map the tangled dependencies within its context, making automated testing nearly impossible. AI-native codebases must shift toward deep modules. A deep module provides a single, highly testable interface while hiding its complex, AI-generated logic inside a gray box. As long as the interface fulfills its test contract, the AI can autonomously optimize the internal logic. This architecture allows agents to work safely and independently without human intervention in the details. This is the agentic engineering loop, forcing alignment up front, slicing work vertically for immediate feedback, and executing against deep modules while constantly resetting context. In this era, the human engineer must stop focusing on writing individual lines of syntax. Your core responsibility is now architectural oversight. You are the director who defines modular boundaries, maintains the testing infrastructure, and ensures the agent remains aligned with the system's goals. As models continue to scale, raw coding capability will become fully commoditized. The machine will handle the physical labor of software production. However, while you can outsource the logic, you cannot outsource the understanding. An AI is a prediction engine. It cannot determine why a feature is worth building or how it should feel to a user. The manual work of coding is disappearing.